In this session, we will cover WaveDFS, the application that's aimed at testing the detection probability performance and detection bandwidth performance, or testing for specific radar pulse performance of an access point that needs to adhere to FCC, ETSI, Japan, or Korea dynamic frequency selection criteria. We will focus on the detection probability test. Once you know how to run that, the detection bandwidth test and the radar pulse generator and false detection tests are just outgrowths of that. In earlier sessions, we covered the concept of clients and connecting to chassis and things like that, so we won't cover that again here. We'll assume that you've already done sessions on running Wave apps or Wave QoE for how to connect to VariWave chassis. So focusing on the detection probability test, we will first connect to the chassis. In order to run the DFS test, we're going to need Ethernet cards and Wi-Fi cards. Now, a couple of things here. The FCC specifications and ETSI specifications require that traffic be run basically downstream during the course of a test. And so we give you the ability to do that. The beauty of this application is that everything can be done turnkey with 2 Wi-Fi ports and 1 Ethernet port if the access point has been set up to emit a channel change announcement over the Wi-Fi interface once it has seen a radar pulse. So let's move through doing this. Card 4 is our Ethernet card, and all we need to do is select it and let everything be automatic. And then on our Wi-Fi side, we're going to use CISO ports. So a CISO port, an 802.11n CISO port, is the only port that can generate a radar pulse. So we'll select one of those and select radar. Then we'll use another port of that same CISO card as the traffic receiver. Now we could use an 802.11n MIMO card or an 802.11ac MIMO card for this traffic. And you can talk with support or the marketing and sales folks to guide you through that. Here we just have these 2 ports hooked together through a splitter into the input of the access point through a 30 dB attenuator, so that these 2 ports will both take care of generating the radar pulse, which is what port 3 will do, and interacting with the access point as a client, as a Wi-Fi client, which is what port 4 will do. We happen to know that this access point is on channel 100, so we'll select channel 100. It'll go out and scan, and we fill in a BSSID. We have an access point out there. So that's all we need to do on the chassis page. So now let's work through the test parameter pages. The detection mode can either be manual, in which the GUI will put up a widget that asks the user if a radar pulse has been seen, or we can choose automatic. In automatic, the monitor port, that port 4, the traffic port, will do a packet capture and look for a channel change announcement to come from the access point when it has seen a radar pulse. We can look for that channel switch announcement in any management frame, or if we have certain access points that put the channel switch announcement in the beacons as a matter of normal transmission, we can look for action frames only. We'll leave it at any management frame. The time interval between test trials should be left at 0 seconds. If you need a little bit longer time between the test trials, you can set that here. And the time interval between detecting radar and sending the channel change announcement, most access points work fine at 2 seconds. We've seen some access points that the channel change announcement comes out a little bit after 2 seconds. So you can, if you are running a test and you think the channel change announcement is there, but the application doesn't appear to be detecting it, increase this number to 3 or 4 seconds. This will just tell you how long the packet capture will be after the radar pulse has been generated for then looking at the packet capture for channel change announcements. The longer you make this number, the slower the test runs. Now let's look at the radar port properties. Remember, we chose port 3 as our radar generation port. We can set the bandwidth to be 20, 40, or 80. we need to set the center frequency of the radar pulse. Now we chose channel 100, which is 5500 megahertz. So we'll scroll down here to 5500 and choose that. That puts the radar center frequency in the middle of channel 100. Then we set the transmit power of the radar pulse. You will need to look at your individual specifications, FCC or ETSI, to determine what the pulse power should be at the access point, then take into account the loss in your cabling setup and your splitter and things of that nature. The way that you can measure it directly is with this widget, a transmit a single radar burst. If you hook up a power meter to where your SMA connector is going to hook into the access point and set your power meter up for detecting 50% duty cycle, you can actually measure the power that's being delivered from the radar pulse generating port to the access point and adjust it to where it needs to be. In this case, we'll set minus 30 dBm. The number that you measure is the number that you should enter here, radar power at DUT, which will print out on the report then for your reference. Next, we go to traffic settings. We're going to leave this as an 802.11ag device, and we'll set the traffic power minus 20 dBm, but we could choose N or AC. If we were using an AC card, the AC button would come up here. And the particular setup I have does not have a DHCP server, so I will choose a static IP address that I know will work for the access point and enter that here. So this is just to get traffic through the access point. This is on the Wi-Fi side. Over here is where the Ethernet client is going to be set up. Again, no DHCP server, so I'm going to set a static IP address. You can choose your traffic parameters down here. Primarily, the only thing a customer will be messing with is intended load and the layer to frame size. You can identify how much channel utilization is being used at any given setting by using this widget. So I'm going to click it and we'll watch it. What it'll do is go out and configure the clients on the Wi-Fi and Ethernet ports, drive the traffic through, perform a packet capture, then come back and measure and analyze that traffic. So if you're testing to ETSI specifications or the new FCC 2014 specifications, there's a certain percentage of channel utilization that you need to meet, and we'll measure that for you. So here we see with the intended load at 4 megabits, the total channel utilization is 10.7%. So if you needed that to be a little bit higher, you would just adjust this intended load until you got the number that you want. The reason that there's not a deterministic way of doing that is that the access point can choose what degree of aggregation it uses, what PHY rates it uses, and so this needs to be just kind of a trial and error approach to adjust the intended load until you get the channel utilization to what the specification requires. That's what that widget does. In the results setting, here we set up where our log results are going to go, whether we generate a report, whether we have custom titles, and then we can put the information in about the DUT that we're testing and even change those labels. So this is all for the PDF report that's going to come out. Now let's go to the probability detection test itself. There are a few things to look at here. We are defaulting to FCC test for 2006, which will have these 6 radar types. These are all defined in the FCC specification. If you want to test for 2014 version of the FCC test, you can click on the button for FCC and choose, and it'll fill in the defaults for now what the new specifications are, which includes the new Type 1 weather radar. Same thing with ETSI for the various years and versions of ETSI specs. You can choose the one that applies to you. Under Japan and under Korea, everything is filled out automatically straight out of the spec. We're going to run FCC 2006, and we're going to shut off most of the tests just to keep things shorter on this video and run only the Type 1 test. So these numbers here cannot be changed. This is what is set in the spec. The numbers up here you can change and select. So here we'll enable the traffic, which we want traffic to be run. If you are having trouble when there's traffic being run, you can turn the traffic off to do some diagnostics. Within the testing protocols, what they do allow is if you're not at a desired detection level, the FCC and others will allow you to run a few more trials. That's what this does. So if you aren't at a detection rate for any type of radar that matches this number here, you can instruct the test to run a few more trials. I'm going to set this down to 1 for now. This over here allows you to choose whether you're going to run all the trials with the radar pulses at the center frequency or moving from center frequency to plus 5 megahertz and down 5 megahertz, or you can choose how many megahertz you move up and down. Again, the FCC does this. They will do their tests not all at center frequency, but at center frequency then plus 5 and minus 5. This is because they know that these OFDM receivers have suppression at the center frequency, so they give you the opportunity to run with those radar pulses off of the center frequency, or you can set to run each trial at a random offset. This is up to the customer to choose. Okay, now that we've set all of this up and we have the access point cabled up to our 2 ports, we can now run the test. By pressing the green button, we'll see that the chassis is reserved, the clients are set up, and now what we'll be seeing is the results of each radar pulse type. So if you are familiar with the spec, you'll know that for type 1, we have to send these type 1 radar pulses while traffic is running. And now what the test is doing is while that traffic is running, which we see over here that we're transmitting 4 megabits a second and we're receiving 4 megabits a second. So we get verification on the right-hand side that the traffic continues to run. And what we're seeing here is each trial, since it's a probability of detection test, we're going to run some number of trials. I think this one is 30. And what happens every time is the packet capture in the card is cleared, the radar pulse is generated, then 2 seconds later, the packet capture is pulled from that CISO port that is the traffic port, and we parse that then for a channel change announcement. If a channel change announcement was found, then it's a pass, and the detect time is the time from the end of the radar pulse to when the channel change announcement frame was found in the packet capture log. And so you can see sometimes the detect time is 0, which means that the channel change announcement actually came out before the end of the radar pulse train occurred, and that's fine. That just means that the access point actually caught an early part of the pulse train. But this gives you an indication of how well the access point is responding to the radar pulses. And we can see here green means that the trial was seen, and the red dot that we saw there was a fail. And now the detection probability test report, the PDF is generated, and we can go down and see that we got a 96% for type 1 using FCC types 2006. And then here is the average detect time, number of trials, the required probability of detection is 60%. We saw 96%. And then here is the detail of each one of the trials. Also on the test, if we expand this, we can right-click on each trial and show the trial data. So this is the detail of what was sent as a radar pulse at that particular time. Now with type 1, they're all the same, so it's not that interesting. But some of the types have randomized variables, and so you can see what was going on. If you're seeing a pattern of failure, then you can go in and look at the details of the radar pulse to see what your particular access point may be having trouble with. And we can see here that we did fail one. We can show the trial data. The trial data will be the same, but if we had certain ones that were failing, we could then see what the characteristics of those failing trials were. Now, if you want to do some diagnosis, you can go into the radar pulse generator, and all the traffic settings and all that will still be the same, but here in the radar pulse generator, you can set up a radar pulse of the type that you're having trouble with. You can vary 2 parameters. Let's say we were having trouble with short pulse widths. So now you could set up all the other characteristics of that pulse and vary the pulse width from some number to another number in steps, how many trials per step, and now you could run a more deterministic test scanning a given variable or 2 given variables across some range to characterize the kind of problems that you're having. As in other tests, there is a results directory. So let me move over here. So if we go to that log directory of VeriWave WaveDFS results, we see the comma separated file information. We'll see the PDF report. We'll see the configuration file so that we could rerun this test again. And we'll also see console information there as well, and the log file of the information that was sent from the application to the chassis. So that's the WaveDFS application suite. The bandwidth detection test runs much like the probability detection test, except all it does is sweep using one of the radar types across the band and tells you the detection capability at each frequency across a given band, either 20, 40, or 80 megahertz. So the WaveDFS application automates your detection probability and bandwidth detection tests by using all of the integrated capability of the chassis, the ability to run traffic, the ability to generate the radar pulse, and the ability to detect the channel change announcement that comes out of the access point, all in one.